Realistically, there will, of course, be friction between your tires and the road surface. And so here now let's consider case two. What happens if you take the turn at a speed greater than the critical speed here? This is the one and only one speed at which friction won't play a role, but if you try to go faster than this, the car will tend to slide up the ramp and friction will appear to oppose that slippage. Friction between your tires and the road will appear to oppose the slippage of your tires up the ramp as you take that turn going too fast. So it'll be static friction, that traction between your tires and the road. So if the tendency of the car is to slide up the road because you're going too fast, then friction will show up to oppose that. So we can conclude that static friction must appear pointing down the ramp, trying to prevent your car from sliding up the ramp. So I'm going to draw a big force of static friction here. I'll kind of exaggerate its length, draw it larger than it would actually be so you can see it clearly. Some force of static friction pointing down the ramp, trying to oppose the slippage of the car up the ramp if you're going too fast. So that's the big change to our free body diagram. Now let's consider the consequences. This new force of friction here is not aligned with our axes, and so we have to break it into components. So here's a rare instance where there is more than one force we have to break into components. We'll need to make this force of friction the hypotenuse of a right triangle with one leg parallel to our z-axis and one leg parallel to our r-axis. So here's the radial component of our force of friction, and here's the vertical component of our force of friction. Look at the effect that it's having. By pointing down the ramp, friction has a component that's pushing the car in towards the center of the circle. There's a negative radial direction component to our force of friction. And there's also a vertically downward component to the force of friction. So friction is pushing to the right and down from this point of view. Now we see that we've got opposite interior angles here and here. So this angle is congruent to our angle theta there. So this is theta and that's theta in this right triangle. And I'll explicitly label these two legs F, F, S, R, the radial component of friction, and then this one here will be F, Fs, Z, our vertical component of friction. So we need to modify our Newton's second law equations. These were the equations for the frictionless case. So we need to rewrite them, adding in additional terms for these two components there. Okay, so now with friction going faster than the critical speed, so friction is pointing down the ramp, trying to prevent us from sliding up the ramp. Let's rewrite Newton's second law. Okay, in the z direction, we have in our sum of forces, the z component of the normal force is up, gravity is down, and the z component of our force of friction is also down in the negative z direction. So two downward forces, one upward force. So there we have it, Fnz, Fg down, and Ffsz down. And from our trig here, we see that this component can be written as Ffs sine theta. So there it is, Ffs sine theta. That's the additional term in our z direction. In the radial direction, we've got Fnr there pointing inwards, and now also helping support it, helping push the car into the turn is this radial component of friction, Ffsr, also in the negative radial direction. So here's our sum of forces in the radial direction. The radial component of the normal force, which was there before, and now here also the inward radial component of the force of static friction. So Fn sine theta, and then for this term right here, it's our force of friction times cosine theta. So I'm going to have FFS cosine theta to get the radial part. And we set that equal to the opposite of v squared over r. All right. So that's the equation that we want. And now an interesting question to ask would be exactly how fast can we go without sliding up the ramp? Now that friction is here to help us, friction opposing our slippage, that'll enable us to go faster than this critical speed. But there will be a limit, of course, because there's a limit to how much force static friction can provide. And so let us set about trying to determine the maximum speed we can take the ramp without sliding up the ramp. So let's make static friction work as hard as possible. We'll set static friction equal to its maximum value, which is mu s times our normal force. And if we don't want to slip, we're going to set our vertical acceleration equal to 0. Let az equal 0. So that means we're setting az equal to 0 here. So this sum of forces will set equal to 0. That'll be what we start working with right here. Net force in the z direction equals 0. And what I'd like to do here is solve this for the normal force. I want to solve for the normal force because between these two equations, we're going to have two unknowns we want to get rid of, or rather two unknowns. We want to solve for that speed here, find the max speed, but the normal force appears in both equations, and we want to get rid of the normal force. Okay. So setting the net vertical force equal to 0, and then making this substitution in for our force of static friction there, setting it equal to its max value. So Fs becomes mu s Fn. That gets us here. If I add mg over to this side, I see on this side I've got Fn on both terms, so I can factor out that Fn. Factoring it out gets us here, and I can divide both sides by this business in parentheses to conclude that our normal force can be expressed as mg over cosine theta minus mu s, the coefficient of static friction, times sine theta. And now this expression I can sub into our radial Newton's second law equation. So I'm going to sub that into here to try and solve for that speed. Okay, so this is our radial N2L equation, and I've replaced the static friction with its maximum value right there, mu s Fn for max static friction. So I'm making static friction work as hard as possible. That means I'm going to be solving for the maximum possible speed here before we break static friction and begin to slide. And then, recognizing that there's an Fn on both terms here, I can factor it out. Also multiply through by -1 to get rid of all these negative signs. That gets us to this line. So I factored out an Fn from these two terms. And now this expression, which came from setting the net force in the z direction equal to 0, I'm going to sub this whole beast in for Fn right there. And then I will have eliminated normal force between our two equations. So here we go. In for Fn goes mg up top and a cosine theta minus mu s sine theta in the denominator. So that gets us to this. I see that there's a m and an m that cancel out. That was this m here and that m right there canceling out. And we're ready to solve for the max. Just multiply both sides by r here, the radius of curvature, and then take the square root. And we've done it. We've got an expression. It's not a pretty expression, but we do have an expression for the maximum speed at which you can take a ramp of radius of curvature r, inclined at angle theta, if the coefficient of static friction between your tires and the surface is mu s. So plug in your values and you can solve for that max speed here. Now, a check on this answer. Can we verify that we didn't make an algebra mistake somewhere? Here's a good thing to do. If we've got a general result like this, we could try and recover an earlier result. We could imagine, say, what happens if we try and go back to the frictionless case? What if there is no friction? Which is easy to do here. We just set mu s equal to 0. Then we would have no static friction. So if we set mu s equal to 0, we'd be kind of recovering the frictionless case. So that means the mu s cos theta goes to 0, the mu s sine theta goes to 0. So if we disappear friction, those are gone. We're left here with sine theta over cos theta, which is tan theta. So if there's no friction, our max speed is gr tan theta, which we proved earlier. We can recover our critical speed. So this result is contained as a special case of this result here. All right, so here's an extension that you can try on your own. We worked out the maximum speed that you can take the ramp without sliding up the ramp. But of course, if you're going too slow around the ramp, you might tend to slide down it. So there might be a minimum speed at which you can take the ramp without sliding down. So if we're going to tend to slide down, then, well, static friction here is going to oppose that. It's going to prevent you from sliding down. So friction will push upwards if you're going so slow that you're tending to slide down. So in our free body diagram, our force of static friction here will flip to be pointing up the ramp, trying to prevent you from sliding down if your speed is less than the critical speed. So if you're going too slow, static friction points up instead. Now, static friction can only work so hard, so it stands to reason that there is also a minimum speed that you can take the ramp before you break static friction and actually slide downwards. So I suggest that you try and work out that expression on your own. Here's the expression for the maximum speed before breaking static friction. See if you can find the minimum speed without breaking static friction.